Main engines. General description. The S-64 Echo has two main engines rated at 4,500 shaft horsepower mounted on top of the fuselage forward of the main transmission. The engines are Pratt & Whitney model JFTD 12 Alpha 4 Alpha, which translates as JFTD Jet Free Turbine Drive, 12 Alpha compressor type gas generator straight through design, 4 Alpha major modifications to complete the engine. Engine symbols and stations. Engine symbols. N1 gas producer, compressor and N1 turbine. Speed given in percent. At 100%, the N1 RPM is 16,030 RPM. N2 free turbine speed given in percent. At 100%, the free turbine speed is 9,000 RPM. Papa is for pressure. Tango is for temperature. A number following Papa or Tango indicates the engine section, i.e. T5, is the temperature at engine station number 5. Engine stations. Station number 1, air inlet at bell mouth. Station number 2, inlet guide vanes. Station number 3, compressor discharge diffuser. Station number 4, gas turbine inlet. Station number 5, free N2 turbine inlet. Station number 6, free N2 turbine discharge. Station number 7, exhaust outlet. Engine sections. Inlet section, engine bell mouth. The bell mouth is shaped. Air inlet is bolted to the compressor inlet case. The bell mouth shape is designed to maximize ram recovery at low speeds. Compressor section. Compresses air for engine operation, also provides a mounting for the number 1 main bearing, roller type. The compressor is an axial flow compressor consisting of 9 rotors and 8 stators. The compressor delivers air to the combustion section at a 6.5 to 1 ratio. Immediately downstream of the 4th rotor stage, compressor air is bled off by an automatically actuated bleed band to facilitate engine starting and increase engine stall margin at low N1 operation. The gas generator turbine drives the compressor. Diffuser section directs airflow through the engine. Also provides mounting for the number 2 bearing, ball type, and the forward engine mounts. The diffuser section located between the compressor and the combustion chamber reduces the velocity and increases the pressure of air into the combustion section. High pressure air is bled from this section for internal and external air bleed systems. Combustion section mixes air and fuel for combustion and directs exhaust gases toward the turbine section. Also provides mounting for the number 3 main bearing roller type. The combustion section is a can-annular burner type, which houses 8 burner cans in an outer case. Fuel is delivered to each burner through a dual orifice nozzle. Burners 3 and 6 are equipped with spark igniters to start combustion. All burners are interconnected with crossover tubes to permit flame propagation during start cycle. At the aft of the combustion section and secured to the combustion chamber inner case is the combustion chamber outlet duct. The outlet duct slightly reduces velocity and straightens the airflow exiting the combustion chambers to reduce drag. A fuel drain incorporated at the bottom of the combustion chamber case automatically drains the combustion section after engine shutdown. The fuel is drained into a holding tank at the lower right of the rear of the cockpit section. Turbine section. Gas generator or power turbine, a 2-stage turbine wheel connected by drive shaft to the compressor and to the component drive gearbox. The turbine discs are attached to the turbine shaft hub with bolts and are separated from each other by the turbine rotor inner seal. N2 turbine or free turbine, a 2-stage turbine wheel connected by drive shaft to the input quills of the main transmission. It also provides a mounting for the number 4 and number 5 main bearings. The exhaust section and contains the N2 accessory drive shaft to the N2 accessory gearbox. The gearbox drives the N2 flex shaft cable and the N2 tach generator. Exhaust section ducts the exhaust away from the aircraft. Component drive gearbox, sometimes called the N1 accessory gearbox, contains the following: the main component drive tower shaft from the N1 shaft, engine starter, N1 tachometer generator, fuel pump, fuel control/governor, engine oil pump on number 1 engine, second stage hydraulic pump on number 2 engine, not used. Engine systems. Engine air bleed systems. The engine has 3 separate air bleed systems. External air bleed provides air from the 9th stage of the compressor for bell mouth and inlet guide vane anti-ice, fuel heater, and cabin heat. Internal air bleed from the 9th stage is used to cool the hot section, contain the flame in the burner cans, and pressurize the main bearing carbon seals. Interstage air bleed via the bleed band counteracts compressor instability, thus preventing compressor stall and surges. It is taken from the 4th stage of the compressor and consists of a bleed strap and linkages. It is operated by a fuel control. Starter system overview. The engine starter motor is located on the lower left of the engine and attached to the accessory drive gearbox. The motor is driven by a 3,500 plus minus 50 psi hydraulic pressure from the hoist pump. The system is protected by a relief valve set at 3,750 psi and the flow regulator at 15 gallons per minute. The start cycle. In a typical start cycle, hydraulic fluid moves from hoist pump through the fuel regulator, through the engine start valve, past the pressure switch, through the starter, and then back to the hoist reservoir. The makeup pump supplies hydraulic fluid to the hoist pump to ensure adequate fluid availability to prevent pump cavitation. Starter circuit. 2 starter switches, one for each engine, are located above the N1 levers on the control quadrant in the cockpit. Start circuit is energized by holding an N1 lever in shutoff and depressing the start switch. The start switch energizes the start valve and the starter control relay through the dropout pressure switch. The start valve allows fluid to flow through the starter. The starter control relay allows the pilot to release the start switch after depressing it for 3 seconds. The start circuit will remain energized until the dropout pressure switch automatically deactivates it, or until the pilot aborts the start. The dropout pressure switch automatically deactivates the starter circuit when the hydraulic pressure in the engine start line drops below 2,000 psi at engine N1 speed of 26 plus or minus 4%. The abort switch can be activated at any time during the start sequence by pulling out on the N1 lever and moving the N1 lever to shut off. If the abort switch fails to stop the start sequence, the start may still be aborted by pulling the starter interlock circuit breaker. An advisory light on the caution panel illuminates to advise the pilots when the starter circuit is energized. The starter circuit is a 28-volt DC from the number 1 DC primary bus. The advisory light marked number 1 or number 2, engine start on, will go out when the dropout switch deactivates the starter circuit. Ignition system. There are 2 identical ignition systems on each engine consisting of high-energy exciter unit, connection leads, and a spark igniter inside the number 3, and number 6 combustion cans. The 2 systems operate independently of each other. The system provides high voltage with 1 to 3 sparks per second from each igniter. The igniters can be heard in the headset when they are firing. Power is from the 28-volt DC primary bus through the 2 switches marked ignition switch number 1 and number 2 on the master switch panel on the center console. Engine oil system overview. Each engine has its own independent oil system consisting of an oil tank, oil pressure system, a scavenge system, a fuel coolant oil cooler, and a breather system. The system is completely automatic, requiring no action by the pilot except monitoring of gauges and caution lights. Oil gravity feeds from the tank reservoir to the pressure pump. Oil is then forced under pressure through the oil filter and check valve. If the oil filter and check valve become clogged, the oil filter bypass opens. From the filter, oil flows through the fuel coolant oil cooler unless the oil temperature is low. If the temperature is low, a bypass routes oil around the oil cooler. The oil then flows to the engine main bearings and the N2 speed sense cable and tower shaft. The oil is sprayed on bearings through jets. The oil then gravity feeds to the scavenge pumps, which force the oil up to the oil reservoir. A breather system allows for the normal system function with altitude changes. Oil tanks. A saddle tank oil reservoir is mounted on the upper left side of each engine. The system has a capacity of 1.6 gallons, approximately 1.95 gallons usable. The tank has a dipstick marked full and add. The oil level must be checked within 15 minutes of engine shutdown. Refer to EAC Maintenance Bulletin 4 through 7 for correct engine shutdown considerations concerning oil leaks. Oil pressure system. The main oil pump is gravity fed and is a single element gear type pump. Normal pressure is 45 to 55 psi at 100% N2. The pump is located on an accessory drive gearbox on the left rear side. The main oil filter is mounted on the pump and is removed and cleaned every 150 hours of engine operation. The filter incorporates a bypass if the filter becomes clogged. A magnetic chip detector is located in the filter cover plate. Metal contamination provides a ground path for number 1 and number 2 engine chip light on the master caution panel. A pressure relief valve is used to regulate oil pressure. This relief valve is adjustable and is used to set the correct pressure on the system. A temperature and pressure sensitive bypass valve regulates oil flow through or around the oil cooler. Oil jets spray the pressurized oil on 13 bearing packs located throughout the engine. Fuel/oil heat exchanger located on the left side of the engine. The engine is cooled by means of a heat exchanger. As engine fuel proceeds from fuel control to engine fuel manifold, it passes through the oil cooler. The relatively cold fuel absorbs heat from the hotter engine oil. The fuel oil heat exchanger works with an associated bypass valve. Oil viscosity causes a higher pressure in the cooler, causing the bypass to open. At high temperatures, the viscosity is less, and therefore the pressure in the cooler lowers, causing the bypass to close. Engine oil pressure transmitter. Located on the engine deck below the engine, it converts oil pressure to an electrical signal, which is displayed on the indicator in the cockpit, and is powered by a 26-volt AC from the number 1 or number 2 AC bus. Engine oil pressure switch, located directly above the transmitter and illuminates the number 1 or number 2 engine oil pressure caution lights when pressure drops below 39 plus or minus 1 psi. Engine oil temperature bulb, located in the exit line of the fuel oil heat exchanger. It transmits oil temperature by the 28-volt DC to the indicator in the cockpit. There is no associated caution light panel segment light. Scavenge pumps. There are 5 scavenge pumps, which scavenge the return oil from the bearings and accessory drive gearbox. The pumps return this oil to the saddle tank reservoir. Breather system. The breather system incorporates a breather valve, which is fully open at sea level and gradually closes at altitude as altitude increases. This helps to maintain oil system pressures and flows similar to those at sea level. The breather valve also has an air-oil separator, which helps remove air from oil. Engine fuel system. Overview. Engine fuel proceeds from the main fuel system to the engine-driven fuel pump boost stage, then through the fuel heater to the engine fuel filter and back to the engine-driven fuel pump main stage. It then proceeds through the fuel control where it is metered, through the fuel flow indicator, through the fuel coolant oil cooler, then to the engine fuel manifold and nozzles. Fuel heater. The fuel heater runs off air bleed from the ninth stage of the compressor and is electrically actuated by a 28-volt DC valve on the air bleed line. The valve is controlled by the heater switch on the fuel management panel on the center console in the cockpit. The fuel heater is used only for suspected fuel icing. Operation: if fuel temp low advisory light illuminates prior to takeoff, the fuel heater is to be used as a precaution. If the fuel temp low advisory light is on and number 1 and number 2 fuel bypass caution light illuminates, fuel icing is suspected. In either case, the heater switch should be placed to heater for 1 minute in every 30 minutes. Note: 1 full minute of operation is recommended to return the fuel filter to its maximum filtration capacity. When using the heater, monitor the engine oil temperature for an increase. Do not use heater during takeoff or landing. If the engine fuel filter light does not go out after about 1 minute of heater operation, the filter is clogged with foreign matter instead of ice. Fuel temp low light. The sensor is located in the hoist well, making it more a part of the airframe fuel system than the engine, but directly affects the decision to use the fuel heater. Whenever the fuel in the fuel lines leaving the main fuel tanks reaches a temperature below 1.1 plus or minus 1.2 degrees Celsius, that is 34 plus or minus 2 degrees Fahrenheit, the light illuminates. The light operates on 28-volt DC from the primary bus. Operation of the fuel heater will not cause the fuel low temp light to go out. Engine fuel filter. This is a cartridge type filter which incorporates a bypass in case the filter becomes clogged. During bypass, a differential pressure switch located on top of the filter will close at a pressure differential of 4 to 5 psi, turning on the corresponding engine fuel bypass light on the master caution panel. Engine driven fuel pump. This is a centrifugal pump which receives fuel from the main fuel system. The first, or boost stage, operates at approximately 20 psi over inlet pressure. The second, or main stage, is a gear-type pump which pressurizes the fuel to 150 to 800 psi, depending on demand, for injection into the engine. The pump is attached to and behind the fuel filter. The fuel control is mounted to the engine-driven fuel pump. Fuel control. Made by Hamilton Standard, the hydromechanical fuel control with free turbine speed sensing unit governs the free turbine rotor speed. It schedules fuel flow to provide the power required to maintain an approximately constant free turbine speed N2 under all loads. The fuel control also schedules the opening and closing of the bleed band to facilitate engine start and low N1 operations. Pilot inputs to fuel control. The N1 lever position determines shut off, ground idle, or speed governing at full forward. The N2 speed trim, beep trim, mounted on the collective lever, sets the desired N2 RPM for each engine. The collective bias system provides approximate rotor load signal to fuel control each time the collective is moved. This helps the fuel control anticipate power requirements to prevent rotor system overspeeds and underspeeds. The bias cables are attached to the mixing unit in the attic. Engine inputs to fuel control. The N2 governor provides the main input for governing of rotor speed and fuel flow schedules. The flex shaft cable provides signals to the governor when N2 speeds increase or decrease from the desired speed. It also provides overspeed protection by shutting down the engine if 115% N2 speed is attained. Fuel control outputs. Schedules fuel flow to the fuel nozzles in the combustion section. Controls the interstage bleed band operation. Controls the pressurizing and dump valve. There are two valves. The pressurizing valve provides fuel flow in the manifold into the primary and secondary and ensures the proper atomization of the fuel being discharged into the combustion chamber. The dump valve drains fuel from the manifold and opens anytime the fuel control is not producing pressure. Fuel manifold contains 8 dual fuel nozzles located in the front center of each burner can. The nozzles are split-type nozzles with a primary jet on the outside for low engine RPM and a secondary jet on the inside. Both nozzles are used at high power settings above 80% N1. Fuel drain. Located at the bottom of the combustion chamber, the drain valve is a reed type which closes when there is pressure inside the combustion chamber and opens when the engine is shut off to drain excess fuel from the chamber. The fuel drains into the fuel drain reservoir located on the back of the cockpit. Fuel flow transmitter. Located in line between the fuel flow and P&D valve. It measures the amount of fuel being consumed by the engine in pounds per hour. The transmitter sends an electrical signal to an indicator in the cockpit. Power is from the number 1 or number 2 AC primary bus. Engine controls. Fuel shutoff valves. Each engine has a fuel shutoff valve located in the center of the attic. This is a mechanical shutoff operated by two handles called fuel shutoff levers on the overhead quadrant. The fuel shutoff levers are connected to the shutoff valve by cables and pulleys. When closed, the shutoff valve prevents any fuel flow to the engine. When the levers are full aft, the fuel flow is shut off. When they are full forward, they open the valves. N1 levers. The N1 levers are located on the overhead quadrant between the fuel shutoff levers. The left one controls the left engine, or number 1 engine, and the right one controls the number 2 engine. They are marked shutoff, ground idle, and full open. The N1 levers provide control of the engine speed, and fuel control is allowed to provide engine power upon demand. Engine power output can be limited by reducing the N1 lever setting to any position between full open and ground idle. The N1 levers also provide engine start button and switches inside the N1 lever assembly to allow the start sequence to proceed or to abort the start. N1 lever must be held against the stop to engage starter. See starter system. Topping governor RPM control in the power range permits scheduling of N1 speed during start and idle. Stops fuel from entering the fuel manifold when placed in the shutoff position. N2 speed trim allows the pilot to set the N2 speed for each engine as desired. Used primarily for fine adjustments to match the engine outputs. Operation is done with switches on each collective marked plus minus number 1 and number 2. The switches provide electrical power to an actuator on the fuel control. The actuator is a DC reversible motor with a brake to lock it in position until another command is received from the pilot. The actuator range is from approximately 94 to 107% N2 speed. The pilot's right seat speed trim switches have overriding authority over the co-pilot switches. Collective bias prevents droop and overshoot due to turbine lag time and the time it takes for the rotor system to speed up or slow down from the collective pitch change. The collective bias is connected to the collective flight controls at the mixing unit and extends to the fuel control by a control cable. The cable controls the collective bias cam on the fuel control. Caution should be taken not to step on this cable during pre-flight. Electrical overspeed protection. There is no electrical overspeed system on the S-64 Echo. T5 indicator. T5 is the temperature of engine exhaust gases at engine station number 5. The indicators require 28-volt DC, which is derived from the DC primary bus, and two 5-amp DC circuit breakers, mounted in the overhead circuit breaker panel and marked number 1 T5 and number 2 T5. The signal from the indicators is self-generating from bimetallic probes, which create an electrical signal as they are heated. The signal is then displayed as exhaust temperature in the cockpit. The T5 indicator is a combination of analog and digital indicator. The analog indicator dial is calibrated from 0 degrees Celsius to 1000 degrees Celsius and graduated in increments of 10 degrees Celsius. The digital indication is graduated in increments of 1 degree Celsius. The indicator has an exceedance light that illuminates at 690 degrees Celsius and ties to the master caution system, which will illuminate a segment marked number 1T5 or number 2T5 on the master caution panel. The indicator also has a recording feature that will activate at 720 degrees Celsius. It will record temperatures and duration of temperatures exceeding 720 degrees Celsius. N1 gas generator tachometer. The indicator marked percent %RPM displays N1 speed in percent. The indicator contains two dials and two needles. Larger dial and needle indicates RPM in 2% increments from 0 to 100. The smaller dial and needle indicates RPM in 1% increments from 0 to 10. The system uses a tachometer generator mounted on the accessory drive gearbox on each engine, with the incorporation of low N1 speed warning. The system becomes dependent on 28-volt DC from the number 1 and 2 primary bus. The N1 system will have one of two N1 underspeed warning systems installed. N1 underspeed warning system. This is the original system. It consists of the two N1 indicators, each with a built-in 1 kHz tone generator that activates anytime the indicator is below 60% N1 speed. The tone can be silenced by a spring-loaded switch marked N1 Disable Audio on the center console. The system is automatically rearmed anytime the N1 speed of both engines has increased above 60%. There are also four red N1 warning lights, two for each engine, that activate when the respective engine N1 drops below 60%. They will remain on until the N1 speed climbs above 60%. There is one for each engine on the glare shield and one next to each N1 lever. N1 Underspeed Enhanced Voice Warning System. This new system incorporates a self-test mode, a chime, and a voice warning. When the aircraft battery is switched on, the system automatically enters the self-test mode. Each engine's N1 system will be tested separately. This function cannot be interrupted or silenced by the pilots. Once the test is complete, the voice warning can be silenced by the oral unknown mute button on the center console. This mute button replaces the spring-loaded audio disable switch. A 700 Hz chime will activate when either engine N1 drops below 65%. A voice warning, number 1 engine out or number 2 engine out will activate if either N1 drops below 59%. Both the chime and the voice warnings can be silenced by the mute button. The system will rearm and reactivate if the N1 climbs above 65% and drops below again, or if a new event, such as the opposite engine N1 decreasing below either 65% or 59% occurs. This system also incorporates the same four red N1 warning lights as the old system. The triple tachometer. The triple tachometer has three needles, number 1 and number 2 engines, N2 RPM, and one for NR, or main rotor RPM. Each needle has its own tachometer generator and functions independently of the other needles. The engines and rotor speeds are displayed in percent RPM. The gauge has an outer dial labeled engine and an inner dial marked rotor. Each engine N2 tachometer generator is located on the top half of the engine and is driven by the free turbine accessory drive gearbox. The rotor tachometer is located on the back of the main transmission accessory gearbox, below the generators and the tail rotor drive shaft. The tachometer generators are all self-generating and independent of aircraft electrical system. Engine oil temperature gauge. The indicator displays engine oil temperature from a sending unit in the exit line of the fuel/oil heat exchanger. The system operates from 28 volts DC. The indicator is calibrated in 5-degree increments. Engine oil pressure gauge indicates engine oil pressure from a pressure sending unit located on the engine deck below the combustion section. The system is powered by 26 volts AC from the auto transformers. The dial is calibrated from 0 to 100 in 5 psi increments. Engine pressure ratio, EPR. The EPR indicates the gas generator pressure ratio as a measure of the power being developed by the engine. This is the ratio of pressure between P-dot pressure and the P5 at the N1 turbine discharge. The EPR gauge has two dials, a large outer dial and a needle calibrated from 1 to 2.5 increments of tenths, and small dial and needle calibrated from 0 to 10 in increments of 1/100th. The signal for the EPR gauges is generated by the EPR transmitters located in the battery compartment. The gauges are powered by 115 volts AC. Fuel flow indicators indicate fuel burned by the engine in pounds per hour. Each engine has its own indicator calibrated from 0 to 4,000 pounds in increments of 100. The indicators are powered by 115 volts AC. Torque meter indicator. There are three identical torque meter indicators, two on the main instrument panel and one on the aft seat pilot's panel. They indicate input torque to the main gearbox as a percent of maximum engine power output for each engine. A torque sensor on the engine rear support sends a signal through the signal conditioners located in the compartment under the right side pilot to the indicators. The system is powered by 28 volts DC. Engine fire warning indicators. There are two separate fire warning systems installed in the aircraft: the engine fire detection system and the fire surveillance system. There are two red master fire warning lights on the instrument panel next to the master caution capsules. These illuminate anytime a fire is detected by either fire warning system. There are also two fire warning lights on the overhead quadrant next to the fuel shutoff levers. These lights will indicate which engine has the fire. The system operated on 28 volts DC from the primary bus. The engine fire detector system has four continuous element fire detector cables, two for each engine, mounted adjacent to the engines. These are heat sensing loops which allow more current to flow when heated by a fire. They are wired in a closed series loop and are connected to a control unit which illuminates the fire warning lights in the cockpit in case of a fire. The system is powered by 28 volts DC from the primary bus. The fire surveillance system has 5 flame detectors for each engine and 1 detector for the auxiliary power plant, APP. The flame detectors are photoconductive cells that react to hydrocarbon and magnesium radiation in a fire. The detectors are connected to 3 control amplifiers in the attic and the same fire warning lights as the fire detection system. An additional fire light for the APP is located on the APP control panel on the overhead console. The APP fire light is also connected to the master fire warning lights. The system operates on 28 volts DC from the primary bus. Auxiliary power plant. Overview. The aircraft utilizes an auxiliary power plant, APP, to allow ground starting of the main engines and to power the aircraft electrical and some hydraulic systems when the main rotor is not churning. The APP located aft of the main transmission. It is connected to the accessory gearbox by a clutch and a draftshaft system. Made by Solar, the APP is a turbine engine. It weighs approximately 79 pounds, develops approximately 72 horsepower, and uses 73 pounds per hour of fuel maximum. The engine has automatic start and control circuitry for operating. An advisory light on the caution advisory panel in the cockpit illuminates to indicate the APP is running. Components. Starter motor. A 28 volt DC motor is utilized for starting, normally powered by the aircraft battery. Oil system. 3-quart system capacity. Pressurized system with filter and gear type pump. Oil filler cap and dipstick must be checked for quantity prior to engine operation. APP clutch. A centrifugal clutch is mounted between the APP driveshaft and the main gearbox. It transmits power from the APP to the main gearbox accessory section. The clutch engages automatically at 76% to 90% APP speed. It can be adjusted if engagement is too slow or too fast. APP control panel. Located on the overhead control panel in the cockpit. It consists of a master switch, a start and stop switches, a temperature gauge to monitor EGT, a tachometer to monitor engine speed. There are 3 warning lights to indicate low oil pressure.
6 plus or minus 1 psi. High exhaust temperature 1070 to 1090 degrees Fahrenheit, and overspeed 110%. These warning lights illuminate to indicate which malfunction has caused the automatic control circuitry to shut off the APP. Master switch is located on the APP control panel. The switch controls operation of the airframe fuel shutoff valve and arms the APP circuit. Start switch arms the holding circuits for the start fuel valve and the ignition exciter, and it energizes the start relay located on the winch well relay panel. Stop switch is pushed closed to abort a start or to turn off the APP. 20% switch controls the start fuel valve. 20% switch is spring loaded and is held in the hold for start position until the APP reaches 20%. The switch is then let go, activating the start fuel and igniter. Start main fuel switch controls the start fuel valve and main fuel valve. In the start position, the main fuel valve will be closed and the start fuel valve will be open. At 40% RPM on the indicator, the start main fuel switch is manually moved to the main fuel position.